Hello, everyone. We're about to get into inverse functions and functions used for the purpose of counting. Before we do that, we have to introduce something that seems so trivial that it just doesn't belong in a math course, but it does. Uh, we're going to talk about the identity function. And the purpose of the identity function is primarily theoretical. Uh, the identity function will appear in proofs and things like that. And it's quite handy to have a name for the identity function because of that. So here's the definition. Given a non-empty set x, the function 1 sub x from x to set x is given by 1 sub x evaluated at x equals x. In other words, we plug an element into this function, we get the same element back out. This is called the identity function on x. Now, for future reference, notice that the identity function is 1-to-1 and it's onto, because essentially we're taking every element and mapping it to itself. Does this element have something, or is this element assigned something by the identity function? Yes, it's assigned to itself. Can any two distinct elements be assigned to the same element over here? No, because every element is assigned to itself. If we have two distinct elements over here, they're going to be assigned to the same two distinct elements over here. So the identity function is 1-to-1 and onto. And we'll remember that because when it comes to doing proofs, this will be a handy tool to have. Okay, inverse functions. Believe it or not, this is really going to be important. Given a function f from set x to set y, the function g, which goes from y to x, so note this, f goes from x to y, g goes from y to x. So given a function f from x to y, the function g from y to x is the inverse of f, denoted this way, f inverse, exactly when this happens. The composition of g with f from set x to set x is the identity on set x. So g composed with f is the identity on set x. And also, f composed with g from set y to set y is called the identity on y, or it turns out to be the identity on y. So f composed with g is the identity on y. But let's look at this a little bit closer. Now let's play around with some pictures and some examples just to make sure that we really get what's going on here. We have a function f from x to y and a function g from y to x such that g is the inverse of x. So here's their composition. G composed with f, and that's the identity on set x. And we also have this. We have g from set y to set x and f from set x to set y. And the composition of the two, I think I'll use a blue pen here. The composition of the two f composed with g is the identity on set y. And you might wonder, well, let's see. It looks like f is to the function g here as g is to the function of f here. So why couldn't we say that f is the inverse of function g instead? And the answer is we can say that. So if g is the inverse of f, then f is the inverse of g. It's that simple. Now let's look at some fairly well-known examples, just so that we can be absolutely sure that we're comfortable with this before we do anything theoretical. Here's a pair of functions that we've had some experience working with. F of x is the exponential function, e to the x. And notice that f maps the entire set of real numbers onto r plus, the set of positive real numbers. In other words, there's no real value of x that we can plug into the exponential function to get 0. There's no real value of x that we can plug into the exponential function to get a negative number. If x is any real number at all, then e to the x is going to be a positive real number. And here, g, the natural log of x, maps the entire set of positive real numbers onto the entire set of real numbers, period. So there's, given any x value in the real numbers, there's some positive real number that we can plug into the natural log of x to get that real number. For example, if we pick 0 here, what number do we plug into natural log of x to get 0? It's 1, isn't it? And if we want to get a negative number by plugging an x value into natural log of x, we pick some x value between 0 and 1. Natural log of all values between 0 and 1 is negative. And let's check and see that these are the inverses of one another. So g composed with f of x, so that's g evaluated at f of x. And g is what? Natural log, so this is natural log of f of x. But f of x is e to the x. And we know natural log and e undo each other. We get x. Now let's do this. F evaluated at g. And f is e to the x. So f evaluated at g of x would be e to the g of x. And g of x is natural log of x, so we get e to the natural log of x, which we know is x. So g and f are well-known inverses of one another. There are a few more things that we'll be able to say about them in a minute or two. Let's look at another example. This is probably a good example. F of x is x cubed, g of x is x to the 1/3. Through function composition, they undo one another and give us the identity. And let's just check. G composed with f of x is g evaluated at f of x. And g is x to the 1/3, so g evaluated at f of x is f of x to the 1/3. And f of x is x cubed. So we have x raised to a power, the whole thing raised to a power, the exponents multiply, and we get x to the first, or just x. And let's look at f composed with g of x. F of x is x cubed, so f evaluated at g of x is g of x cubed. And g of x is x to the 1/3. And again, the exponents multiply, we get x to the first, or just x. So these two functions, x cubed and x to the 1/3, are inverses of each other, as if we didn't know. But these are some examples that we want to look at just to get a feel for what an inverse does. What we're about to do next, we laid the groundwork for in one of our previous lectures. But suppose that f from set x to set y and g from set y back to set x are inverses of one another. Well then, we have f going from set x to set y and g going from set y to set x being the identity function, which is 1 to 1 and on to. Oops. I'll just write it like this. I beg your pardon. G composed with f from set x to set y is 1 to 1 and on to. Well, let's see. If we have the composition of two functions that are 1 to 1, if f from set x to set y composed, well, if f goes from x to y and g goes from y to x, and the composition is 1 to 1, that means the first function has to be 1 to 1, right? So f has to be 1 to 1. And we have the composition of functions, g composed with f, where f goes from x to y, and g goes from y to x. The composition is onto the second function always has to be onto, doesn't it? But there's more, because not only is G the inverse of F, but F is the inverse of G. So we can draw a diagram like this, where G goes from Y to X and F goes from X to Y, and their composition, F composed with G, which is the identity on Y, is 1-to-1 and onto. It's the identity function on Y, so it has to be 1-to-1 and onto. So F composed with G is 1-to-1 and onto. Now, what do we know about the composition of functions that's 1-to-1 and onto? The first function right here has to be 1-to-1. G must be 1-to-1. And if we have the composition of functions that's onto, the second function must be onto. So F must be onto. This tells us something. And I'll have to erase this picture, but I don't think we need it anymore. Okay, I'll do it this way. Here's the point. If F from X to Y and G from Y to Z are inverses of one another, then F from X to Y has to be 1-to-1 and onto. And G from Y to X has to be 1-to-1 and onto also. We've just shown that. What we just proved laid the foundation for the theorem that we're about to prove. And it's a fairly important theorem when it comes to counting things. And the theorem says this. Suppose that we have a function f from set x to set y. Then f has an inverse g from y to x if and only if f is 1-to-1 and onto. And we just showed 1/2 of this theorem. We just proved 1/2 of this theorem already. We just proved that if f is a function from x to y, and there's a function g from y to x, such that g is the inverse of x, then f is 1-to-1 and onto. We just proved that. What we have not proved is that if f is 1 to 1 and onto, then it has an inverse g from y to x. So let's write out the proof of this theorem. So here's our function. Given f from x to y, f has an inverse g from y to x if and only if f is 1 to 1 and onto. So here's one direction. There exists a function g from y to x such that g is f inverse, implies that f is 1 to 1 and onto. We just proved this. So now we got to turn it around and go the other way. Okay, here we are taking it in the other direction. F from x to y is 1 to 1 and onto, implies that there exists a function g from y to x such that g is f inverse. So if a function is 1 to 1 and onto, it's going to have an inverse. And that's what we're going to prove right now. And what we're going to have to do is define the function g, or f inverse. And I guess to get started, we'll just notice that this is our hypothesis. Okay, let's try this. Pick an element y and set y. Since the function f is onto, then there has to be an element x in set x such that f of x equals y. And we'll call that element x of y. Now, we've used the fact that f is onto, but we haven't used the fact that f is 1 to 1. But we're going to do that right now. And what the fact that f is 1 to 1 tells us is there can't be two different x values in set x that get paired with the element y. There can only be one. there's exactly one element x, and we'll call that x of y, just so that we know for future reference, if we see x of y, this is the unique element in set x that gets paired with element y by the function f. So I think this is how we're going to define our inverse function. Our inverse is going to be such that y gets assigned the element x of y. Now let's make sure this works. We've defined our function g, which is our prospective inverse of function f. We just have to make sure now that things work the way they're supposed to. Let me do it the other way around first. F evaluated at g of x of y. No, I like this way better. Let me rewrite this as g evaluated at f of x of y and note what f evaluated at x of y is. F evaluated at x of y is just y. Now, g evaluated at y, what is that? We have it defined up here. G evaluated at y is the unique element x of y that is assigned to element y by the function f. So g evaluated at y is this unique element x of y. So check. That works out exactly the way it should have. Now we just have to reverse the composition and make sure that works as well. Okay. F composed with g evaluated at y. Let me rewrite this with friendlier notation. So this is going to be f evaluated at g of y. G of y, well, remember what that is. That's the element x sub y, where x sub y is the unique element that f maps to y. So g of y is x sub y. So this is f of x sub y. And by definition, x sub y is that unique element that f pairs up with y. So g composed with f is equal to the identity on x, and f composed with g is equal to the identity on set y. Hence, g is the inverse of x. So if we have a function f from x to y that's 1 to 1 and onto, that means there's a function g from y to x such that g equals f inverse. Okay, that's our proof.